Okay, so we've learned a little bit about animation in a traditional sense, but how does this all translate to digital animation? It turns out that, at least at the basic level, we leverage a lot of the same properties. So basically, in computer graphics, animation happens if we can redraw our scene quickly enough. That was really messy. Animation happens if when we redraw our scene quickly and repeatedly. Okay? The other key point is we introduce changes. So we saw that in the previous example. I draw this circle at a new location, I draw it at a new location, and it looks like it's moving across the scene, even though it's not moving across the scene, right? You're just drawing at different locations. So in processing, we have our event system to make this work. And it's basically set up to call our draw function regularly. And this gives us our ability to do animation. We can rely on that. If we know the draw is going to be called regularly, we can make subtle changes. We get animation for free. It turns out that how quickly it calls that function you can set manually with a frame rate command. We've used that a couple times now. But you can basically tell it how often to call a draw, and then it'll set up the event manager to do that, maybe a timer. This sets the target, how many times per second draw is called. And the caveat is that it might be slower, right? Remember, with an event system, if you take longer than if you want to call it 60 times a second, but you take longer than 1/60th of a second to draw it, it can't keep up. It'll drop the event, so they don't build up, and you'll draw less than your target if you take too long. And we've done that in a previous exercise. You can see how that works. So I guess the question we have then, it's a computer. We can tell it to go as fast as we want. And one question that comes up is, how fast is enough? How often should we be drawing? What should we set that frame rate to? What should a target be? Classic film, like we talked about in the previous lecture, was 24 frames per second. So 48 on, off, 24 full frames every second. Now, classic animation, and I mean like really classic, like Bambi or Snow White, really old stuff, was often less than this because of how expensive it was to make each frame. So I'll say commonly less. You could even have it down to 12 frames per second, and you can notice in some old animation it looked really choppy. Okay. Traditional TV, cable television before we went all digital, was targeted at 60 hertz. If you know about your power system in North America, our power system is at 60 times a second AC cycle, so they matched that. And generally we got 30 frames per second out of that because of how it was interlaced. And we've learned a little bit about that before, but it would draw even frames, odd frames, even frames, odd frames to manage some of the bleed over effects. And because of persistence of vision, you didn't even notice it. This is the Ntsc standard, which is North American Television Standards Corporation. I don't know what it stands for, but NTSC is a North American television system. You also had a variant for countries that use 50 hertz electricity, okay, which would give us 25 frames a second interlaced. and this is PAL format. There's more going on than the frame rate. It turns out because PAL is slower, like fewer frames a second, they can put more data into those frames, and PAL actually had better color reproduction than NTSC, but NTSC had much better motion because it was faster. So you had that really cool trade-off, and when I was a kid, people would argue, like, oh no, PAL is better because of the color. No, NTSC, look at the motion, and that's a debate that people used to care about. Of course, it's solved now. We fixed it. So TV found that, when you grew up, TV was about that. That was good enough for TV. The common target we come across now is 60 frames a second. Is 60 frames a second. Now, before LCD monitors and you had CRT monitors, you could easily set them, because it just had that gun moving around, you could set them to much higher frame rates, much higher refresh rates. You just make it faster. We can't do that anymore. Currently, we're mostly limited by the monitors. So many current monitors, unless you spend a lot of money on it, are limited. Limited to 60 hertz. So 60 frames a second. Hertz means cycles, right? So 60 frames per second. In their hardware, they're limited. They cannot go faster. So if your program runs faster, you can't see the difference. Now I'm not going to get into it. There are some programs, some TVs or some monitors that'll claim they'll blend them together differently, and it's pretending to make it, and you might notice like some of the jarring effects get a little smoother, but it's all fake. The monitor is limited to 60 frames a second. You're only getting 60 frames a second. Now what's cool about all of this is I want to mention briefly this one, interlaced, where it draws even and odd. And remember, in all these cases, we still have the scan line, right? Where it's drawing the lines in order. I should probably draw that a little nicer. It's drawing them in order. But they do it fast enough that it scans fast enough that persistence of vision is why we see a solid scene. We don't see those scan lines. Go back to your previous lecture where we show the slow motion video, or link to it somewhere, and you can look at that. It's really cool. Okay. So we try to draw up to 60 frames a second unless you have a really high speed monitor. That's what we want to do. Now the common approach to programming this, we've learned about double buffers already, but I'm going to mention it again because that's really the way that it works. So the common pattern here is we use a double buffer. We've already learned about why and what this means for tearing and that kind of thing, but you can imagine you have your monitor here. This is your monitor. And your video card has it linked to a buffer, a draw buffer. I'm going to draw this. But in the video card, we actually typically have two buffers. Okay? Because we're doing double buffering. Now, the one that we're drawing currently, we'll call this the front buffer. And the one we're not drawing is called the back buffer. Okay, it's the back buffer. We're not drawing on it. We're not showing it right now. So we draw this, and you can imagine to draw the other one, we just move the pointer and we swap. But I'll come back to that in a second. You could, draw this, no, draw that, no, draw this, no, draw that. So what we do is we use this double buffering to prevent tearing and other artifacts. Because remember, tearing is a very specific artifact where you're blitting and you have an old and new. But you could have a half-drawn scene with the background drawn but the front not drawn, and you'll get a different artifact. So to prevent tearing and other artifacts, you draw to the back buffer. Now remember, the back buffer is the one that's not currently being tossed to the monitor. I'll underline that. Okay, it's a vocab. It's not currently being tossed to the monitor. It's called your back buffer. So you draw to the back buffer, and then you swap them. So depending on your implementation, You could either blit, depending on the hardware, it will do a rapid copy like we've talked about in earlier lectures, like old hardware, or more currently what will happen is they'll move that draw pointer, like I said, where like, oh no, draw this, it's just a pointer. And then when you're drawing to the back buffer, they swap those pointers. So you modify those pointers, and you can actually do it without blitting. The monitor just grabs from somewhere else, now you're drawing somewhere else. So you can save that blit if you do the bevel buffering that way. So in code, it commonly looks like this. Draw, and then GL, swap buffers. You call that command, and it'll do that pointer change, or depending on the hardware, you might have to do it. You might have to do a blit. I should probably write that in my notes. Blit if necessary, or preferably just change the pointers. Right, just change these pointers and everything should just work. These days, this is not like a big feature. It's typically on by default. The places where I've had to do blitting myself was with really old hardware or custom widgets where they don't expect you to double buffer, that kind of thing. Okay, so that's basically the introduction to how digital animation works. Should be no surprises here. I'm just connecting the dots. We just tell our computer to draw things faster or slower, and if we draw it fast enough, we get that illusion of motion, just like with the film. Okay, good. So this is a good place to take a break. We'll come back and learn about how actually the first ways that animation can work digitally.